Hi, this is Professor Challa Vijay Kumar. I teach quantum chemistry at the University of Connecticut, USA. And here is an answer to your question from one of the students from my class. I thought I would post this on the YouTube because there's lots of students who ask very similar question, may have one. And this is actually a very legitimate, very confusing issue that needs some additional clarification as well. So the introduction of the question raised is a very good one, is in the topic term symbol under atomic spectroscopy. We use a lot of different symbols and a lot of different quantum numbers and a lot of different nomenclature, and sometimes it can be very, very confusing. And so hopefully this video would help some parts of that. So why should we study this topic? The term symbol, that is topic term symbol. And the question was that to obtain term symbol, we need lots of different quantum numbers, and what are they and how do we obtain them? So as usual, I always ask why we bother with this and why should we study this. So as usual, so the answer is the following: term symbols define the exact electronic states that are allowed in atoms and molecules, and it could be ions as well, or radicals. And the energies of these systems depend not only on the principal quantum number but also other quantum numbers as well. And that's the beauty of this, and that's the reason for this. And part of the reason why they depend on other than the principal quantum number is that the electrons have momentum, angular momentum. And there are three kinds of angular momenta that we can expect. One is the orbital angular momentum, which is what can be viewed as the electron zipping around. But that's not how we visualize it. But quantum mechanics allows the electron to have only certain orbital angular momenta. So this is inherent to the system. And also, quantum mechanics dictates that each electron have spin angular momentum. So this is the other kind of angular momentum. One is the orbital angular momentum. The second is the spin angular momentum. And the third is the sum of the spin and orbit. Spin orbit angular momentum. And all these three vectors point in some direction. We know precisely the values of these vectors, but not their directions, because of the uncertainty principle requires when you know precisely the value, then you cannot know those direction, or there will be some uncertainty in the directions. So the total angular momentum, orbital angular momentum, and the spin angular momentum for each electron is defined. Now, if you have only one electron, this is all you worry about. But if you have more than one electron, then you have to sum these angular momenta of each of the electron to get the total for the atom or the molecule. Okay, so we have angular momenta, we have their z components, and then we have totals of each of these and the totals of totals. That means total orbital angular momentum, total spin angular momentum, total z component of the spin angular momentum, and then total of all these from all the electrons put together into the atom or the molecule. So there are a lot of different kinds of things. That's why it gets very confusing. So we'll deal with one electron system first and get through these symbols, and then we'll ask what happens for a second electron if we introduced it, and then a third, and then a fourth, and so on. So this is why we need to study this stuff very clearly, very carefully. And these symbols and the terms means states, energy states, are necessary to explain the spectroscopic problems. So in an experiment, we see a certain number of lines, and we want to assign what that line corresponds to. If we want to do that, we need to know all these different states allowed. Because the orbital and other momenta couple, either they can cancel out or reinforce themselves, so the energy of the electron changes. So you get different states, you get different lines, and you get splittings and all that sort of thing. That's the reason we need to look at this term symbol. And what is the basis for the origin of these different states? As I was alluding to just moments ago, that the electron has certain spin, and so it has spin angular momentum. It has some orbital motion, so it has orbital angular momentum. And so then you can sum these two, you get a total angular momentum, and each of these three have z components. So this is the case for every electron in the system, and some cancel away, some reinforce each other. So we need to think about how these are coupling, how only certain states, certain mixtures are allowed by quantum mechanics, and we will define them very quickly and what states are allowed. And then transitions among these states are again controlled by what's called selection rules. So you create a ladder of states, and then the selection rules define which transitions are allowed, which transitions are not allowed. So based on that, you only get a certain number of lines. You do not get all the possible lines, because certain lines are prohibited by quantum mechanical restrictions or selection rules. And so what quantum numbers do I need to worry about? Well, you need to worry about a whole bunch of things that are shown here. And on this slide, I have not shown the total angular momentum to keep things slightly more simple. And my regular lecture in the course deals with those details quite well. So I would say we'll put it off for a few minutes, and then we'll visit that in a short time. So the first thing as I said, orbital angular momentum. So the orbital angular momentum is controlled by azimuthal quantum number, small l, for each electron. And for each electron, we have a certain value of l. And the value of l depends on the value of n. So we already discussed that, the principal quantum number. So each n gives rise to a certain number of l values. So if we have an electron with a certain principal quantum number, we know what l values are allowed. Okay, so this is the azimuthal quantum number, L. Then the z component of that orbital angular momentum has a quantum number called magnetic quantum number, and that is m sub L. So m sub L, this is the z component. Every time we write a z component, we write sub, right? M sub something. Then spin quantum number, and controls the spin angular momentum of the system. And that's given the symbol small s. Okay, small l for the azimuthal quantum number, and magnetic quantum number small m sub l, small l, and for the spin quantum number we have small s, and then the z component of the spin angular momentum has the spin quantum number for the z component as m sub s. In all these cases, we only need the l value, the lowercase, and we need the small s value. And from this, we're going to build everything else. We'll build j, and 2 s plus 1 l sub j term symbol will be built from that. The z components, angular momenta, and the corresponding quantum numbers are not necessary for our discussion. But we will point this out to show that there are these as well. So the confusion arises because of, people are not very clear whether they mean quantum number or they mean the actual value of the angular momentum. And it also confuses because we don't talk about total value or the z component, or total is it total value is orbital per spin, or is it total orbital or total spin? So there's so many different things involved, so we need to be very clear. We have a single electron, we have only one value of L, we have only one value of S, and we have only one value of M sub S. And so very simple. You have a second electron introduced, then you have another set, and then you have to couple the two. So the coupling creates more additional states as well. So this is why it is an issue to be dealt with very carefully. So all the z components are given m sub value or L sub value or S sub value, like that, so on and so forth. So we'll keep that out of business. And the z component becomes important only when you want to know whether the vector or angular momentum vector is pointing up or down, and it's precessing because of the uncertainty in its direction. But it could be a pointing above the xy plane, or it could be pointing below the xy plane. So in a multi-electron systems, obviously you have a number of small l values, and so now we couple the orbital angular momentum vectors by specific rules. And one of the rules says total orbital angular momentum when you have more than one electron is obtained by summing the value of L values of individual electrons, and you get what's called L max and L min. And L max gives you sum of all the L values, and L min gives you the highest value of L minus sum of all other values of L. So once you have L max and L min, you can now construct allowed quantum numbers for the total orbital angular momentum quantum number. Mouthful. And that's explained in the slide in my regular lecture. How do you get that? And then you have the z component. So it is m sub L. So for the total orbital angular momentum quantum number, z component, and that's given m sub L. And the sum of all the magnetic quantum numbers of the electron is m sub I. So we keep that, z component. Then you have spin angular momentum is given, a total of that is given symbol capital S, and is obtained by summing all the individual spin quantum numbers of each electron. Each electron is allowed plus half or minus half. And so if you have 3 electrons, plus plus plus, or plus minus minus, or plus minus minus plus, whatever. So all different possibilities, and everything is on the table. So you assign them based on what L values they have. And if you have a paired electrons, then you have to have opposite spins. One will have plus half, the other minus half. If you have unpaired electron, you customarily give plus half. Okay, and then you have a z component of this, and that is m sub s. And if it is total, then you sum all the m sub s values. That is 1 electron, 2 electron, 3 electron system. Then you get the total value of s. Total value of m sub s. Excuse me. And then you have total angular momentum. So this is what I was alluding to in the previous slide. The total angular momentum means that orbital angular momentum plus spin angular momentum put together is a quantum number j. This j is very important for us because that tells us what is the value in 2s plus 1 L sub j. What will be j there? And so j is L plus S, and L plus S minus 1, and L plus S minus 2, etc. up to L minus S. All these values of j are allowed. So in other words, what are we doing by this? By doing this, we are summing the value of L. So we have different values of L, which is total orbital angular momentum quantum numbers. Then you are adding the total spin angular momentum quantum numbers to it. And then you're subtracting one at a time. 1, 2, 3, 4 out of that to get L, until we get L minus S. So all these different states where the spin angular momentum and the orbital angular momentum total values are coupled. And so, and this is why the system gets complicated when you have more than one electron in the system. So J is defined that way. And then you have the z component of the total orbital plus spin angular momentum, that is m sub j. And so m sub j is given 0, plus minus 1, plus minus 2, you get plus minus j for even values. And you get 0, plus minus 1 half, plus minus 3 half, plus minus 5 half, etc. until plus minus j for the odd values of j. So to write the term symbol 2s plus 1 L sub j, we need j. So j is defined this way. And L is defined by summing all the small values of L. You get different values of L. And so you get L max and L min. From that, we calculate the allowed values of L. And capital S is the summation of all the spin corner numbers of each of the electron, and it could be either plus half or minus half, and so you get that. So you get 2s plus 1 L sub j. We define 2s plus s. In 2s plus 1, we define L, and we define j. So in summary, identify the unfilled states. Ignore the filled states because they have no net contribution to the angular momentum, and it's 0, and everything cancels out because all electrons are paired up, and so everything, boom, goes to 0. So identify the total angular momentum corner numbers, identify the total spin angular momentum corner numbers, so that is capital S, and then and the corresponding z components are not necessary, you just write them down. But now write the total angular momentum corner number, j, and that are allowed. So you can create a whole bunch of L, S, J values. So this should hopefully help a little bit in clarifying all different states, different symbols, different terms or words are used to describe the basis for the term symbol. Thank you.